In this video, we discuss contour integrals, definition of contour integrals, and examples of contour integrals. How to evaluate contour integrals in complex analysis. To define line integral or contour integral, we suppose that the equation z equal to z of t, where a less than or equal to t less than or equal to b, represents a contour c extending from the point z of a, that is z1, to a point z of b, that is z2. We also assume that f of z of t, that means if we evaluate this f on the contour, that should be a piecewise continuous function on this interval. So this can be considered as the composition of f and z, two functions f and z, that can be written as f of z of t. So as a function of t, this should be continuous, piecewise continuous. We define for this is the case, we define the line integral or contour integral of the function f along the contour c in terms of the parameter t, that is integral over c f of z dz. So this is the this represents the contour integral of f along c, that is equal to, that can be evaluated using integral a to b f of z of t times z dash t dt. So this is the definition of contour integral or line integral. As a remark, we can observe that the sum of this integral is same as that is integral of this f plus g can be written as integral of f plus integral of g. So using in fact this is a definite integral in reals. Even though this is this involves complex numbers, then we can consider the integral as integral of the real part plus I times integral of the imaginary parts. So if we consider such integrals as real integrals, or we define this integral using real integrals, so all the properties of real integral can be extended to this integral as well. And the interesting fact on this this contour integral is, if we define a contour in the other direction or the opposite direction, such as if z equal to z of t is a contour with a less than or equal to t less than or equal to b, then you can define another contour. We call that as some z prime, that is equal to z prime of t, that is defined in terms of minus t. This is a dash of t is nothing but z of minus t. So we define the contour in the other direction. Okay, we define the contour in the other direction. Then if we replace this t by minus t, then the interval must be minus b less than or equal to t, t less than or equal to minus a. So this will be the if we take t in this direction or this interval, then this is a dash is nothing but if we call this a c, this is the contour, then this will be considered as minus c. So this traces, or the points on this contour traces c in the opposite direction. So if this is the case, we have integral over c f of z dz can be considered as in fact this is integral over minus c f of z dz. We can prove this is true that using the definition of the integral that we have written here. So that is we can write integral over minus c f of z dz can be written as since minus c is this, we can write this as minus b to minus a f of z of minus t and d by dz of z of minus t as well. Okay, when you simplify this using the properties of the definite integral, we will get this as minus integral minus b to minus a f of z of minus t times z dash of minus t as well. This minus sign is due to the derivative of this. The derivative of this is z dash t dt with minus sign, so that can be taken out. So this can be written as by property substitution. The substitution as tau is equal to minus t, we can write integral over minus c f z dz is equal to minus integral a to b, minus integral a to b. This is f of z of tau. If you substitute minus t is equal to tau, you can write this as f of z of tau times z prime of tau. Okay, z prime of tau d tau. Okay, so then I can write this which is same as in fact this can be written as minus of this is integral over c f of z dz. Okay, because this tau is a dummy variable, so a variable of integration that can be replaced by any other quantity, then you will get integral over minus c is same as integral over c. Okay, so this is another interesting remark on this definite this line integral or contour integral. Another fact is, if we have two contours, say this is our c1 in the direction and this is another contour c2, then you can construct c as c1 plus c2, that is c1 along with c2, and c is obtained by adjoining the c2 in the tail end of the c1. Then you can easily prove that integral over c f z dz is same as integral over c1 plus c2 f z dz, that can be written as this integral over c1 f of z dz plus integral over c2 f of z dz. Okay, so this is what we called additive rule. So some rule can be extended and additive rule can also be extended to this. So the proofs of this is included in the textbook as well in the section 40. So please go through it. Our intention is to prove the problems of or evaluate the integrals of this type. Okay, so first of all we have example 1, that is if I is equal to this integral over c, this z conjugate dz, where c is the curve, z is equal to 2 times e to the power I theta, where theta varies over minus pi by 2 less than or equal to theta less than or equal to pi by 2. So this describes the circle of center 0 and radius 2, because if we consider this mod z, then we will get that is 2. So this mod z, because modulus of e raised to I theta is equal to 1, so this implies mod z is equal to 2 from the point z equal to corresponding to the point theta is equal to minus pi by 2. Whenever theta is equal to minus pi by 2, this will be e raised to minus pi by 2, so that will be minus 2i, so that is here minus 2i. It's a part of the circle with radius 2 from this is part of the circle with this point. This is our 2i. So this is our the direction is along this way, because theta varies from minus pi by 2 to pi by 2. So this is the part of the circle which we called this is c. So integral over c, we can evaluate this integral. I is equal to integral over c z conjugate dz, that can be written as integral over minus pi by 2 to pi by 2, because this is the variation of the parameter theta. Instead of taking t, we have taken theta here, then this will be z conjugate will be 2 times e to the power minus I theta. Okay, so this is the conjugate of this z is this one, then conjugate is 2 times e raised to minus I theta, and that times z dash t, we need to multiply it with the derivative of 2 is e raised to I theta, so that will be 2 times e to the power I theta as well. Derivative of this e raised to I theta is e raised to I theta itself, then this will be e raised to I theta, then we have d theta, and this can be simplified as 4 can be taken out, then minus pi by 2 to pi by 2, this e to the power minus I theta times e to the power I theta, so that will be 1, so we can write it as 1 d theta. So this will be theta varies from 4 times theta varies from minus pi by 2 to pi by 2, so that will be 4 times. First of all we have pi by 2, then minus of minus pi by 2, that is pi by 2 again, so this will be pi. So the answer will be we have I as well, this is the derivative of this will be 2 times I, right? The derivative of 2 raised to I theta, if z equal to this 2 to the power, please note this, you need not miss this I z dash, that will be z dash of theta will be I times 2 times e raised to I theta. Okay, so there is I here, so we have I here, I can be taken out, so here we have I, here we have I, then we have this is 2 times, this is pi by 2 plus pi by 2 is equal to pi, then this will be 4 pi I. So this is the value of the integral. Okay, so another example is given in the textbook. There are more than a couple of examples are discussed. So please go through it. So if you have any confusion, we will discuss in the live interaction.